Welcome back. Let's look at the following problem. So a three-sided rectangular pen is to be fenced in against a wide building, as in this picture, using 100 feet of fencing as shown. So basically, we are creating a pen with 100 feet of fencing, and the question is the following: find the maximum area of the pen and the corresponding length and width. That is, the question is, with this 100 feet of fencing, what is the maximum area we can enclose within the pen, which is built like this. So let's say the X is the width of the pen and L is the length of the pen. So then notice that the perimeter of the pen on the side of the building, we don't need fencing. So the perimeter of these three sides would be x plus L. So that's 2x plus L. So 2x plus L is the perimeter of the pen where we have to use the fence. And so we have that 2x plus L is equal to 100. So this is our constraint. This is telling us how much fencing we have, and that also tells us what is the perimeter of the pen. And what are we trying to maximize? Well, we are trying to maximize the area of the pen, and the area of the pen would be length times width, which is L times X. Okay, so to understand the problem, let's look at some observations. So here is the pen, and the constraint is that 2x plus L is 100. So let's look at different values of X and L and see what area we get out of them. So if I pick X to be 0, then L would be, well, if X is 0, then L is 100. And of course, the area of the pen then is just 0 because X is 0. So pretty much we are, when X is 0, then we are pretty much creating a pen with just one side, which is going to enclose 0 area. So imagine that you put the entire fencing by the building. What if X is 50? Well, if X is 50, then the total of the two widths here. So if X is 50, then 2X would be 100. And if 2X is 100, then L is 0. So if I pick X to be 50, then L would be 0, but then again, the area would be 0. So if L is 0, that means that we are putting the entire fence on a straight line perpendicular to the building. Now, what if X is 10? Well, if X is 10, then 2X would give me 20. So on these two sides, I have to use 20 feet of fencing, and then L would be 80. Well, in that case, the area of the pen would be 80 times 10, which would be 800. What if we pick X to be 40? If X is 40, then the two sides, the two widths here would be 80, and L would be 20. So in this case, the area would be 800 again, 40 times 20, so that's 800 again. So I hope you can see that we can pick X and L in many different ways. So there are many choices for the length and the width of the pen, satisfying the constraint here. with many different areas. So we want to pick the width and the length in such a way so that we have maximum possible area enclosed in the pen. Okay, so we need to build a pen with 100 feet of fencing as shown. We want to know what is the maximum possible area we can enclose in the pen. And the constraint here is that since we have only 100 feet of fencing, the perimeter of the pen, 2x plus L, must be equal to 100. And so from this constraint equation, we get that L is equal to 100 minus 2x. The area of the pen is L times x, and where we can replace L by 100 minus 2x, which is going to give us this function 100x minus 2x squared. So that's the area function. That's the area of the pen as a function of the width x. Notice that, let's do a reality check. So that is, notice that x cannot be negative, so x is greater than or equal to 0. But also notice that x couldn't be bigger than 50, because if x is 50, then 2x is 100 and L would be 0. If I pick x bigger than 50, then L would become negative, right? So x couldn't be bigger than 50 either. So we have this area function where x has to be non-negative. In fact, here I could say x is non-negative. Of course, when x is 0, the area is 0. And also the length has to be positive or non-negative, whichever I pick here. So then, so this quantity here would be non-negative, but this would mean that x is less than 50. So this is the domain, and this is the area. This is the area function that we want to maximize on this interval. So again, we find the derivative of this function, which would be negative 4x plus 100. And the critical point would be when this would be then 25, because that's when x is 25. That's when the area that's when the derivative is 0. So we got only one critical point, and let's look at the second derivative. It is negative 4. So second derivative evaluated at 25 is also negative 4, which tells me that the area function is concave down at 25, which means it has a local maximum at 25. But since this is the only critical point, that's got to be the absolute maximum. So we see that when the width is 25, in which case the length would be what? Well, if the width is 25, remember the length is 100 minus 2x. So if x is 25, then 100 minus 2 times 25, that's 50. So L would be 50. So when the width is 25, the length is 50, and then the maximum area of the pen will be 50 times 25, which is 1250. So 1250 is the maximum possible area that we can enclose within the pen. Okay, so this is it. I'm going to stop the video here. In the next video, we will be looking at some other examples.